Welcome to STAT200. This is our video lesson on the normal distribution since we were unable to get to class due to bad weather. So this has to do with the famous bell curve, and one reason why it's useful is because if I take a histogram if I create a histogram from a sample of data that's based on physical measurements, it also applies in other situations. The histogram often is symmetric, like the one pictured here, or has a kind of a bell shape. The example below represents the distribution of heights in inches of 300 randomly chosen adult males. So the mean's somewhere around 59 or 60, and the heights range up to a little over 70 inches and down to a little below 50 inches. So because this distribution is symmetric, our empirical rule would be valid for the population represented by the sample. But this gives us a clue as to where the normal distribution comes from. It's a symmetric distribution that has a bell shape. In fact, if I convert my histogram, the previous one, to a relative frequency histogram, where the heights are no longer counts, but represent the fraction or proportion of the data in each class, and I overlay that with the bell curve, the formal bell curve for the population model that was actually used to generate the data, we get a picture like this, where the shape of the histogram very closely matches the shape of the bell. And remember, in a relative frequency histogram, the heights indicate percentage. In this case, we did a little bit more in the scaling. The heights are scaled to make the total area of the bars equal to 1, because what we're doing really is using the areas to represent probability, as we saw when we considered probability functions for continuous variables. In fact, this makes the normal distribution, as we'll see, a probability density function. So where does this come from? The shape of the normal distribution is described by this ugly function here, which you never have to know much about, but it is important that there's only two parameters that control it. The standard deviation, sigma, is used in two places, and the mean, mu, is used in two places. And so, given only those two numbers, it fully controls the shape of the bell curve. What do these things control? The mean simply controls the location of the peak. As I move the mean up, the peak moves upward, so the mean here is around 150. I move it down, the mean's about 100 now, and I move it down further, and the mean's down to 50. The mean is, for the normal distribution, also the mode and the median. It's the peak of the curve, and it's symmetrically distributed about the mean. Well, what does the standard deviation do? The standard deviation controls the width of the curve. Remember, when we computed standard deviations, a large standard deviation meant the data was widely dispersed, and a small standard deviation meant the data was pretty clustered tightly around the mean. Well, the standard deviation for the bell curve has exactly the same meaning. A very small standard deviation means the data is clustered about the mean. It's tightly centered on the mean. And a very large standard deviation means it's spread out. Now, why does the height of the curve change when I change the standard deviation? Well, if I make the curve narrower, I have to make it taller so that the area stays the same. This is because, again, this is a probability density function, and it's area under the curve that matters, and so to be a valid probability density function, the total area has to be 1. And so when I make the bell curve narrower, I need to make it taller, and when I make it wider, I need to make it shorter to keep the total area to 1. Now, the standard normal distribution, the picture is static. It has a mean of 0 and a standard deviation of 1. And notice that we're using the population parameter symbols, mu for the mean and sigma for the standard deviation, because the normal distribution models a population. And so here's the picture. Between -1 and 1, remember, within one standard deviation each way, we get about 68% of our values according to our empirical rule? Well, about 68% of the area is contained within plus or minus 1 standard deviation. If I go 2 standard deviations up and 2 standard deviations down, that's most of the area under the curve. That corresponds to about 95% of the curve. And then notice when I go out to 3 standard deviations and minus 3 standard deviations, I get almost all the curve, almost all the area, about 99.7%, as we saw when we learned the empirical rule. And this is actually, it's the normal curve that actually gives us the empirical rule, as we'll see when we work with it. One reason why we care about the standard normal distribution is back in the days before powerful computers and calculators, we had to generate tables of area under this curve. And you'll still find these tables of area under the standard normal distribution in the back of your book, and in the Hawk system you'll be asked to use those tables to compute probabilities. But as we said, the normal distribution is a probability density function, a PDF, so when we compute probabilities related to the normal distribution, we don't look at the height of the curve, we look at the area under the curve between two limits. On the standard normal curve, we compute the probability of our value falling between two limits as the area under the curve between those limits. So here's an example. The probability of finding a value between -1 and 1 on the standard curve is about 68%, or 0.68. Notice the actual number is 0.6827. And notice that corresponds not to the height of the curve, which is 0.4 at the top, but to the area, the shaded area under the curve here. If I go out to 2 standard deviations positive and 2 standard deviations negative, now notice the probability of getting this is actually a z-value since it's on the standard normal curve. The probability that x falls between -2 and 2 is 0.9545, or about 95%. More technically, 95.45% probability of finding a value in here, because that corresponds to 95% of the area under the bell curve. And then if I go all the way out to 3 standard deviations above the mean and 3 standard deviations below, that's plus or minus 3 on the bell curve, I get my 99.7%, or 0.9973 to be exact. And then of course if I push out even further all the way to 3.5 below the mean and 3.5 above, I get almost all the area, 99.95% of the area. Actually, the bell curve goes on forever. The normal distribution never stops, but once we get beyond about 3.5 standard deviations, there's very, very little area left, which means the probability of finding a value up here becomes vanishingly small. Okay, so to use the standard normal curve, or to use the tables in the back of the book, we need to convert from a variable's natural scale to the standard normal scale. And we do that using z-scores that we encountered back in chapter 3 when we practiced with the mean and standard deviation. So we can convert from the natural scale of a normally distributed random variable to the standard scale using z-scores. If x is the value of the variable where it's normally distributed with a mean mu and a standard deviation sigma, then I get my z-score as x minus the mean, that is x minus mu, divided by sigma. That's how far the value is from the mean in terms of standard deviations. We scale it by dividing by the standard deviation. So for example, if x is a normally distributed random variable, that's what this symbol means, with a mean of 270 and a standard deviation of 35, and my x value is 290, then the z-score for that x value is 290 minus the mean, 290 minus 270, divided by 35, or about 0.5714. Often z-scores are rounded to 2 places, but we'll stick with our standard 4-place notation here. What does that mean? It means that 290 is about a half, or about 0.6 standard deviations above the mean, because I have a positive z-score. So here's a illustration of mapping from the variable's natural scale. Here I've laid out the scale for 270 as a mean and 35 as a standard deviation. 270, if I go up 35, I get to 305. If I go up another 35, I get to 340. If I go up another 35, I get to 375. So that corresponds to going up 1, 2, 3 standard deviations. And similarly going down. 270 minus 35 gets me to 235. Minus another 35 gets me to 200. Minus another standard deviation gets me to 165. So these values are located 1 standard deviation below the mean, 2 standard deviations below the mean, and 3 standard deviations below the mean. And we can see we can do intermediate values. For example, if I'm half a standard deviation below the mean, that means I'm at 252.5, because if I take 252.5, subtract 270 and divide by 35, I'll end up at minus 0.5. And similarly, I can sweep through the scale here. So this z-score is actually a way to map us from the natural scale of the variable here from about 165 up to 375 onto the z-scale. So then we can use the standard normal curve to work with it. Well, how do we do these areas under the curve? We use the TI-84's statistical functions to be able to calculate these probabilities. So given that we're on the standard normal curve with a mean of 0 and a standard deviation of 1, we can compute the probability that the z-value falls in any interval between a and b using the calculator function NormalCDF. We put in the low limit and the upper limit, and it returns the probability. It gives us this probability. To reach this function, we use the buttons on the calculator. Second vars, which is actually the distribution button, and then we select the second entry, NormalCDF. Once this appears on the screen, once NormalCDF appears on the screen, we enter the lower limit, A, followed by a comma, and then the upper limit, B. And then we don't follow it with a comma. We just follow it with a closed parentheses if we want to be nice. And then we hit enter. Enter. And what will be returned is the probability that z falls in that range. So for example, to compute the probability that x falls between 80 and 110, where x is normally distributed with a mean of 100 and a standard deviation of 10, we first convert these limits to the z-scale. So I convert the lower limit, I'll call that ZA, is 80 minus 100, negative 20, over 10 is negative 2. So negative 2 is the z-score corresponding to my lower limit. The upper limit, I'll call it ZB. I take the upper limit, 110 minus the mean, divide by the standard deviation, that's 10 over 10, or 1. So to find the probability that x falls in the range from 80 to 110, that's going to be the same as the probability that z falls between minus 2 and 1. And I can find that by running NormalCDF with minus 2 as the first entry and 1 as the second entry. If you do that following these instructions here, you'll get 0.8186, or about 81.86% of the values on the original distribution fall between 80 and 110. So your turn. See if you've got the idea here. Using both these slides and the notes that you received in class that are posted on D2L. Suppose that the weight of my sheep, I've got a large flock of sheep, and that population weight is normally distributed with a mean mu of 84 pounds and a standard deviation sigma of 12 pounds. If I choose one of these sheep at random, Determine the probability that the selected sheep will weigh between 78 and 96 pounds. In symbolic terms, that question says, given that the random variable W representing the weight is normally distributed with a mean of 84 and a standard deviation of 12, compute the probability that the weight falls between 78 and 96 pounds. So please pause the video here, work out your solution, and when you have it worked out, when you've computed the probability using z-scores, then you can continue the video. Okay, so hopefully you've done that. You've found the answer. Let's compare solutions. So first I convert my limits, my 78 and 96, to z-scores to put them on the standard normal curve, the standard bell curve. So 78 minus the mean, 78 minus 84 divided by 12 is negative 1/2, negative 0.5. And the upper limit, 96, to convert that to the z-scale, it's 96 minus 84, 96 minus the mean, divided by the standard deviation. That's 12 over 12 is 1. So I can find the probability that the weight falls in this range by finding the probability that z falls between minus 0.5 and 1, and I get that with normal CDF, minus 0.5 comma 1, and enter. And you should have gotten an answer of 0.5328. Now, based on the notes we passed out in class, you can also use normal CDF with 4 numbers. Instead of converting to the z-scale, you can put in the lower limit, the upper limit, and then tell normal CDF what the mean and standard deviation are. But it's important, whichever way you do this, you put the numbers in the correct order. It's always low limit, then upper limit. Otherwise, you'll get a negative answer, and what's coming out is probability, and probability's never a negative number. And then if you use this form, the last 2 numbers have to be the mean and standard deviation in that order. Okay, so for homework, please work to complete the exercises in Lesson 9, Introduction to the Normal Distribution. Study the material in sections 6.1, 6.2, and 6.3 of our textbook, and study the corresponding tutorials in the Hawk system. When we get back into class on Tuesday, we'll do lots of practice with these different ways of computing with the normal distribution, and we'll have a brief quiz on this. But I'm also going to post a quiz on D2L under quizzes, so please look for that. I'll send you an email when that's available. It'll be a quiz on basic probability using the material we covered the last time we met on Tuesday. Okay, well, that ends this lesson.